Hello, my name is Ali Reza, and I'm the product manager for the UGS module in ETAP. If you have already watched the video for the introduction of UGS FEM engine in ETAP 26, you may be aware that we have introduced a new calculator for calculation of cable derating studies in ETAP 26 based on finite element method, which is called UGS FEM. So in this video, we are gonna demo the UGS FEM engine calculation against CIGRE technical benchmark 880 for different test cases that are covered in that benchmark. So I'm gonna start with uh, study case 0 of that technical benchmark because it has like different scenarios and different settings. So here I have the summary of the test case that I wanna demo. And for this test case, we have a one core cable XLP insulated at 132 kV. And this is made of copper, and it includes like conductor screen, installation screen, and an aluminum sheath, and an HTTP sharing. So as the first step, I'm gonna add this cable to the library, because the first step to define a cable in ETAP is that you make sure that the cable is added to the library. So here I have ETAP 26. I'm gonna go to reference page and just create a new cable library, and let's call it cable CIGRE. Okay, so we are gonna go to cable library here and define the setting here. So I'm gonna add this as a new cable. So the cable is in metric system. I'm gonna select metric. The frequency is at 50 Hertz. Let's call the source name CIGRE case 0, or we can call it CIGRE. For the type, it is like copper, and the cable is one core. The installation is XLP, so let's select PE here, because yeah, XLP here. And then for the voltage level, let's type 132, and the rest should be good. So I'm gonna hit OK. I have the definition of cable here now, and then I'm gonna define the details of the cable in the physical page of the cable. So let's add one new size in the physical page and see what we have here. So cross section of the cable is like 630. So here for the size, I'm gonna type 630. Let's go back to the data sheet here. So you can see that cable comes with like conductor and inner semiconductor layer. So in ETAP, whenever there is a semiconductor layer on the conductor, we need to add it up to the conductor layer. So it means that at the end of the day, for conductor diameter, we have 13.3 as the conductor overall diameter, and we have an additional 1.5 semiconductor layer on this. So 2 times of this value makes it like 3, and so it's gonna be 33.3. So here for the conductor OD, I'm just gonna type 3.33, and it is in centimeters. So for the OD, we need to convert it to centimeter. Let's go back to the datasheet again regarding the insulation thickness. Again, we have the insulation here, and we have an external semiconducting insulation layer over the insulation layer. So again, in ETAP, if there is like a semiconductor layer on top of the insulation layer, we need to add it up together and iterate it. So if we add these two, it's gonna give us like 16.8 as the thickness. So here we have, for the insulation, it is in millimeter. So I'm gonna type 16.8. Then what else? Cable, the next layer comes with a metallic sheath, and the sheath is like made of aluminum. So the thickness of that sheath is 0.8. So let's do this. I'm gonna go back to ETAP again one more time. And here for the sheath, I'll select aluminum sheath here, and the thickness is gonna be 0.8. And let's see what else we have. So we have the aluminum sheath, and the last layer is like HDP oversheet or jacket or serving of the cable. So it has a thickness of 3.5. Again, I go back to ETAP, and for the jacket, we can select PE instead of HDPE. The parameters are the same. So for the jacket, we have 3.5, and the overall diameter of the cable gonna be 75.5 millimeter. Okay, so 3.5 for the jacket, and cable overall diameter in centimeter gonna be 7 centimeter and 55 millimeter. Okay. Also, regarding the conductor construction, let's check the cable again. It's copper stranded conductor, so we can move on with like round conductors here for the conductor construction. We need one more data to add, and that's gonna be the DC resistivity at 25 degree. So most of the cable data sheets generally provide the data for the DC resistance at 20 Celsius. So we need a conversion here to convert this value from 20 to 25, because ETAP is based on American standard, and in American standard generally it's reported at 25 degree. So to make this conversion, I'm gonna do this calculation here. So I have the alpha 20 value for copper as 3.9 to the power of minus 3. So initial temperature is 20, the secondary temperature is 25, and I have the resistivity at 20 as this value. So it's just a simple equation that we write to convert it from 20 to 25, and if we run it, it's gonna give us like 2.8856. This is ohm per meter. So in ETAP, we need to convert it to micro ohms per meter. So if I multiply it by 10 to the power of 6, it's gonna give me 28.856. So let's go back to ETAP again, and let's type 28.856 as the DC resistivity for the cable at 25 degree. So regarding the rest of parameters, I won't need them for the cable thermal study. If you're running a different study, definitely you need to enter those values. So let's hit OK and save the changes that we made. Okay, now that I have defined the cable properties in the cable library, I'm ready to add the design for the UGS presentation and move on with the calculation. So I go to the cable system group here and click on this underground raceway system. If you have already watched my previous video, you know that here we have two types of methods here for this study. So since I'm using the new engine, I'm going to select finite element method here and hit OK. So now the presentation is created for me. So I go to edit mode, and here from this AC cable, I just add a new AC cable to the presentation. So for this AC cable that I added, I'm gonna pick the library entry that I defined a few minutes ago. So this is the library entry. The only size we have is 630, and we hit OK. All right. Then we hit OK again, and we can see that the cables are now added to the presentation. So for this setting, for the first case, which is case 01, there are touching cables laid in trefoil formation directly buried at the depths of 1 meter from the center of the trefoil. And here we have the coordinates for the center of the cable. So I go back to the ETAP again. We know that for the direct buried case, we have a direct buried raceway here, and I grab that one and drop it here. So for this case, this is as if the cables are directly buried in the soil. However, I still need this one so that I can place the cables inside of this raceway. And you know, this is just a placeholder. The raw value for this raceway and the soil gonna be the same at the end of the day. And let's make sure that we move it to the to this step, so I can fit the cables probably better inside the raceway. And that's okay. Just make it large enough here. And let me put these cables into a touching trefoil formation and grab the cables together and move it here. So I need to place it at the depths of 1 meter. So I just zoom in, make it close to the ruler, and just move this down a bit so we make sure that we are at the depths of 1 meter. Yeah. And once you double click on this raceway to open its editor, you can see that here we show the coordinate for the center of each of these cables here. So we have 102, 95.4. We compare with this one. We are very close with what we have here. All right, this looks good. So here are the parameters for the soil. The maximum allowable temperature for the conductor is at 90, the ambient is 20, and the thermal resistivity of soil is 1. All right, I go back to the ETAP here. First of all, I open the soil. So I need to make this 100 because in ETAP, we need to enter the values for the thermal resistivity in forms of Kelvin centimeter per watt. So I multiply that 1 by 100, which gives me 100. This is the ambient temperature as 20, and this is the maximum temperature for the cable. I hit OK. Don't forget that for this case, because this raceway intends to be similar as the soil, so I need to change this also to 100. And hit enter. Okay, that's good. All right. So this FEM engine for now, it only supports steady state temperature calculation, which means that I need to give the cable a loading and then based on the loading that I have entered, the temperature for the cable system gonna be reported. So let's go back to the calculation again. So for the case that they are grounded at both ends, it says that the ampacity of cable by CIGRE is 821.8. So let's first make sure that we are selecting she's as grounded at both ends. All right, this is grounded at both ends. And here, let's just type 821.8. All right, I hit OK. So I'm ready to run the calculation. Before I do that, just a quick review of what we have here. So for finite element method, we have maximum number of iterations plus precision. We generally don't touch these two. We follow the default values here. And we have the heat transfer coefficient. So for a normal condition, I mean natural airflow, this 10 is generally the correct value. So if you have your like forced cooling, this value can be generally higher. But for natural airflow above the ground, this 10 is like a reasonable value. Okay, I hit OK and run the study now. Let's give it a name, case 0-1 CIGRE. All right. Okay, we can see that for this case, we are reporting like 91.5, while a standard was reporting like the maximum temperature for this case is like 90. So if we make the current here a bit smaller, let's say 880 probably, and let's run the calculation again. Yeah, we are at 990.8. So if I just make this smaller, let's say 812, something like that. Yeah, so I need to play around with this value to find the exact value which gives me like the maximum allowable temperature. Yeah, this should be good enough, like 850 if we assume that we are at 90 temperature degree. Okay, so this is for the first case. So we can see that we are generally very close. Let's say if we are reporting like 850, then 850 minus 820 gives us like 5. So 5 divided by 820. This is like 0.6 deviation. This makes sense because this finite element method is generally based on numerical calculation, while CIGRE TB880 is based on standard equations. So a small difference is expected. However, this difference is not expected to be too much. All right. For the second case here, this is single point bonded, which means that we need to change the setting for the sheath. Let's call it like case 0-1. Okay, for this one, let me first enter the ETAP ampacity. Almost 850 amps. So which makes the max deviation as 0.6% different. Okay. For this case, let's use this 880. And so I go back to edit mode here, open the cable one more time, go to the loading page, make this 880. And in the physical page of the cable, I need to change this one to open to for the case that it is like single point bonded. All right. I hit OK again. I go back to the study mode. Let's give it a new report name here, like case 0-1-1 CIGRE. Okay. Yeah, so here we are at 88. So I need to increase the loading a bit. Let's say I make this 890 probably and run the calculation again. Yeah, 890 something. It's gonna give me the maximum temperature for this case. 892 is actually too much. So yeah, 891 should work maybe. Yeah. Yeah, nice. We are at 90. The maximum temperature here is 90. So for this case again, if we wanna calculate the maximum deviation, I mean the difference between ETAP and the CIGRE. So we have 891, 880, and let's divide it by the 880. So yeah, 1.25% something. So again, this is pretty much expected because oh, by the way, this here it's actually 886. So 880 is like the rounded down value. So if we move on with 886, it's gonna be even smaller. So yeah, for this case, we can see that it's also very close. Okay, so for the second case, the cable is installed. The same cable, I mean, it's installed uh, in a in a series of dots that are in trefoil format. So let's quickly also model this case again. I'm gonna create a new presentation, use the finite element method again, hit OK. All right. So this time I need to model the case that we have ducts installed inside the soil. So for this case, again, I need to use this duct bank here that I have. So let's add the duct bank to the presentation that I have and make this a bit, let's zoom out a bit. So make sure we are on the, all right. All right. And I'm gonna make this large enough so I can place the ducts inside the raceway here. Again, it's a placeholder for this case. It's a placeholder for placing the ducts in this presentation. So I'm gonna add a duct here. The they are like HDPE ducts. So yeah, they are HDPE ducts, and the outside diameter is 14 centimeter, and the thickness is like 10 millimeters. So let's do this. We make this selection as other because it is like HDPE. It has a lower thermal resistivity compared to PVC. Okay. I set the outside diameter as 14 centimeter, and for this thickness I'm gonna type 0.3. Yeah, Okay, let's hit okay. All right, I have the duct here. So you can see that you have the option to select the conduit fill material or the duct fill material here. So we move on with air, and we use the default thermoresistivity for the air here. All right. Okay. This should be at the depths of 1 meter for the center of trefoil. Okay. I'm gonna make a copy of this conduit and paste it. Okay, let's make this a bit larger so I can like put the conduits there, and then I'm gonna make this again to the regular size. All right. Okay, and one more in touching condition. All right. Let's again, this is just a placeholder, and row value is gonna be the same for with the soil, so it doesn't matter how large is the raceway here. Okay, now I have placed them in the same setting as the benchmark. Then for this one, I need to change the row value to 100. And for the soil, this is 90, this is good. I need to also change this one to 100. All right. Okay. And now let's add the same cable that we had before, cable 1. We already defined it for the other presentation. So all we need to do is to drop the cables to each of these raceways, to each of these conduits. So yeah, let's place them inside the conduit. All right. So for this case, the ampacity that is calculated by CIGRE is 680. Let's go back here and go to the loading page one more time. Make this 680 and make sure that we are using again grounded at both ends, because for this case the cables are grounded at both ends. All right. And now we're good to run the calculation. Okay, let's call it case 03 CIGRE. Actually, it's case 02. All right. Yeah, so for this one, we are reporting like the maximum current is like 92.6, which means that I need to reduce the temperature for this, I mean the loading for the cable a bit. So let's make this 670 and run it again. Yeah, almost there. So for this case, CIGRE is like reporting 680 while UGS FEM is reporting 670. And by the way, when cables are in the dock, for FEM calculation, actually it matters that whether this is touching with the walls or not. So let's do a quick comparison here. I'm gonna move the cable to the center of the duct so it doesn't have any contact with the wall, and I'm gonna run the calculation again. All right. Yeah, so you can see that temperature is now a bit higher compared to the previous case, and the reason is that when the cable is touching with the conduit, it generally has better heat transfer with the conduit wall, because it's like transferring the heat through conduction because of that direct contact, while when we place it in the middle of the duct, it's all air around it. So there is no more direct contact with the solid material here, which makes the temperature a bit higher. But at the end of the day, again, for this case, the deviation is pretty much small, and I just want to emphasize that this is much expected because of the difference in the nature of these two methods. But I would probably move on with the finite element method for my calculation instead of standard method, because it accurately catches the details of the system based on physics law. So I would say, to me, finite element is generally more reliable compared to the standard methods. And for the last case that we have here, this is the case that cables are installed in the duct bank. This time, duct bank itself has a different thermoresistivity value. So let's also cover this one very quick before we end up this presentation. So I go back to the presentation that I have here, create a new one. So we are again at the depths of one meter. All right. Let's move this to the 1 meter here and zoom in. Let's add a duct bank to the raceway. So for this case, the dimension for the raceways are also provided by the CIGRE. So width is 655, height is 325. All right. So width is 5, height is 32.5. All right. The raw value for the raceway, which is like made of concrete, is 0.8, which makes it here as 80, again, because of the unit conversion. All right. I have the raceway added there. As the next step, I need to drop the conduits here. So for the conduits, they are PVC conduits with outer diameter of 12.5 and thickness of 3.2. Okay, so this is PVC. This is good. 12.5, and thickness gonna be 32. All right. Okay, I have this one added, and let's see the distance between the ducts is 16.5. All right, so for this one, I'm gonna make it 1625. All right, let's create a copy of this one again, paste. Let's paste it somewhere that we have enough room. All right. So for this one, it's gonna be 3275, 16.25. Okay, and we need one more. All right, 49.25, 16.25. Okay. So yeah, I have added the conduits to the presentation now, and I'm ready to run the calculation. So for this case, CIGRE says that ampacity is like 634. So let's add the same cable again, the cable that we already defined to the previous presentations, and drop them to the bottom of this conduit. Okay, and one more. All right, nice. So I need to change the loading again, make this 634. And this is grounded at both ends. All right. All right, this looks good now. I also, let me quickly change this to 100. Okay, 20 and 90. This should be good. Yeah. Let's run the calculation now. And we call it case CIGRE. Okay. Yeah, so for this case, we are reporting 92.4, while ETAP is like, while CIGRE is like at 90. So let's make this 630 probably a bit smaller. 630. Now let's run the calculation. Oh, by the way, I guess I just missed something. So this should be at the depths of 1 meter, while I have placed it at a different depths here. So let me just move this a bit up. Make sure the center of the cables are at the depths of 1 meter. All right, let's try one more time. Okay, very nice. So for 630, it's giving us 89 for the middle conductor as the hottest conductor. So let's just make this a bit higher, similar to the CIGRE. And yeah, we're almost there. So yeah, for this case, the difference is very negligible compared to the other cases. Yeah, so yeah, as you can see, this engine is a very solid engine. It's capable to run any type of calculations. For example, something that standard cannot handle is that when uh, uh, backfill layer is added on top of the raceway to help improve the heat uh, dissipation inside the soil. So standard methods generally cannot handle that. Let me adjust the height for this one. So it covers like, okay, let's do this. I'm gonna move this to the very top and just expand this here. All right. Yeah, so this backfill layer, there's a layer that is generally added with lower resistivity to improve the heat dissipation. So let's run the calculation as the last step for this case. And you can see that heat, the temperature of the cable has improved because of the backfill layer that you have here on top of the raceway to improve the heat dissipation. This is something that standard method cannot handle, but using this UGS FEM, you can run definitely everything as long as they are like either installed in the ducts or directly buried. And as the very last step, I just wanna show you the couple of plots that are reported through the FEM presentation after running the calculation. So the advantage of this method is that it can report the temperature at every point within that presentation. As you can see through this heat map, you can see the temperature at every point. If you hover on different locations, the z value that you see here is actually the temperature of the corresponding point. Okay, this is very exciting. And here we have a different plot, which is for the configuration of the presentation. This shows like similar to what you see on the UGS side, but with more details here. So if you zoom in, you can see that you see the cable cross section here with different layers, and this is pretty much similar to the cross section that you have on the cable data sheet. So you have stranded cables, you have XLP insulation, you have aluminum sheath here, and P serving plus race phase and that. Yeah. So this is it for this video. We covered together the verification and validation of CIGRE case 0 using UGS FEM, and hopefully in the next videos that I'm gonna prepare later, we will be covering the whole CIGRE TB880 using ETAP to see if for the rest of test cases it's still valid or not.